Okay, so this is lecture number 9 of EE 503, and today we are starting probability discussions. So our topic is from now on involving some probabilistic discussions. Okay, so let me get started with terminology. What do I mean by terminology? Some definitions. Sample space, outcome, event, and probability. Again, this is just a review because most of EE students have taken two courses, Introduction to Probability course and Random Processes course, Introduction to Random Process course in their undergraduate years, covering all of these topics actually. This is the basics of probability. So this is just a reminder. So what's the sample space? So there is a probabilistic experiment. So let me also write this. Probabilistic experiment. So there is maybe a random event. Let me say experiment one more time. Let's say that what can it be? Assume the classical example is you're throwing a die. Okay? Die has 6 faces. Then outcome is outcome. So this is one of the experiment result. Let's say number 1. Face number 1 appears. Outcome of the experiment. Face number 2 appears. Face number 3 appears, and as you have guessed, face number 6 appears. Okay, so these are individual outcomes. I have 6 possible outcomes if I throw a die like this. Okay, this is called the result of an experiment, outcome, random experiment. So what is a sample space? Sample spaces, let me write it over here. This is shown by, in general, some kind of an S, a figure like this, an S figure. So this is a set of all outcomes. So this is 1, 2, 6. Okay? So set of all outcomes. Okay. Now, how about event? Event is, so these are denoted as A, let's say. Event is a subset of, subset of this set, okay, S, sample space. Sometimes we think sample space like the universal set. It contains all possible outcomes, like the universal set. So A is a subset of this set, universal set. But this is called sample space actually. So what can be some examples for this? Maybe an empty set is an example. Sometimes we show empty set by this, right? Or this can be set of 2, 4, 6 even numbered faces, or this can be sample space itself. Okay, remember from earlier set discussions, a set S is a subset of itself. Okay, an empty set is a subset of it. So if I have 6 elements like this, I can pairwise combine them. I can combine them in a triple wise, okay? 1, 2, 3 and so on, like over here. So this forms all possible, A is then one of those subsets. If the subset is not equal to S, it's called a proper subset. Maybe you can remember it like that. So as you can see, in this probabilistic experiment, there is some outcome. This can be actually any experiment. Maybe there is a football match going on. This is the win or lose indicator of that match, so on. Maybe this is the time when the first goal occurs and so on. Okay? So there's a random experiment going on whose outcome, so what's a random experiment? Whose outcome, the result of this experiment, cannot be understood or cannot be totally determined in a deterministic way. Okay? There is no deterministic mapping. Okay? So what is probability? Probability, this is the important part. So probability, maybe I should emphasize this. Probability is a mapping from sets, so these are the events, to real line, to let me be more specific, to 0, 1 interval. In other words, probability, sometimes we use this. A set is here, let me write A then, is from this event, let me write event space for this in order not to introduce further terminology, to 0, 1 interval. Okay, so A is an element of event space. So events are, as you see, these one is subset of one of these, let's say. Okay. So there are some issues. So this is a definition of probability at the end. Okay. But the important thing is for now, maybe. Now, as you see, there is a curly bracket over here. So this indicates that somehow this A is a set, and this is like a set argument. Probability is mapping this set to a real number. Okay. Very good. Now, that's all for now. But let me have, this is called Kolmogorov's axiomatic definition for probability. The issue is, now I have some events, I have some outcomes, etc. Then how do I set these probabilities in such a way that it will be useful for our purposes? So Kolmogorov's axiom number 1, probability of, let me write it like this, is equal to 1. Let me see. Oh no, this is, let me use my notes. This is 0. Greater, probability of A is greater than or equal to 0. Probability of S, sample space, is equal to 1. Probability of A union B is equal to probability of A plus probability of B, provided that A intersection B is empty set. Okay. Now I have such a case. So provided that means if this condition is satisfied, then this is true. Okay. So these are the Kolmogorov's axioms, and this third axiom is the additivity axiom and so on. And what else? So what we see. Now these are sets. Okay. So there is a mapping from the set to a number, mapping to a number. So what I see is that if these sets are disjoint, okay, the intersection is equal to 0, then I'm just adding up these probabilities. So sometimes probability is called a measure of the set. How big is the set, you may say. Okay, how big? So I'm assigning a number to the set, assigning a number to the set. If the sets are disjoint, you are just adding up those numbers. This is our axiom. Okay. So all of these probability results are derived from these three axioms. Okay. There were in the history of probability some many trials how to define probability in a useful manner, or how can you simplify these definitions, and Kolmogorov's axiom at the end, it has finalized the problem. Now I would like to focus on some set operations right now, because as you see, as soon as I define these sets, now I'm also using union of these sets. So what do I have as a set operation? Obvious, A union B, A intersection B, and we may have B complement and so on. Unions, intersections, and complements. Okay. So again, I have a universal set S. I have some elements. I'm taking the union of these elements, intersection events. I am taking the union of these events, intersection of these events, and so on. Okay. I can take complements. So what do we know? For example, we know something like this. You will remember maybe De Morgan's laws. What are these? A intersection B union C. This is A intersection B union A intersection C. Okay. Let's say A union B intersection C. So what's going on? Well, these are sets, as you can imagine. So I have ABC, some sets. This is my, let's say, universal set S. As you see, some subsets of these S's indicated as ABC. Okay. So what is the set? B union C. This is not a proof, but this is a sketch, as you see. B union C intersection A. So I get this part, I get this part. Red part. B union C intersection A. So this is A intersection B, this part. Union A intersection C, this part. Something like that. Also you get the other one, B intersection C. B intersection C. I'm just overdrawing this. B intersection C, union A. I have something like this, blue part. So this is A union B, whole thing, A union B, intersection A union C. So this whole thing, intersection by this, so I get this, blue part again. So how do I remember these De Morgan's laws? Well, if you are an electrical engineer, you have seen such operations in digital logic course also, unions and intersections and etc. So how I remember it, not from that course, but from this. I consider this some kind of an addition. I consider this some kind of a multiplication, okay? So this is a distributive property of multiplication over addition. So this is 2 times 5 plus 6. This is 2 plus 5 plus, as you see. 2 times 5 plus 6, this is 2 times 5 plus 2 times 6, okay, something like that. But the De Morgan's laws are surprising. So there is distribution property, first one, of union over, intersection over union, and the otherwise, distribution property of union over the intersection. So it's both ways. But if you remember one of it, the other one will be automatically written, okay? So it's always valid. This distribution property is valid. Now, as you can imagine, we will be doing some set operations. So this is the reason that we are doing De Morgan's law study, intersection, complement, and so on. So the issue is the following. Now, I should assign these probabilities in such a way that at the very beginning, for example, if I assign probability of A as 0.1, this is at 0.2, A union B for consistency, it should be assigned as 0.3. Otherwise, I have a problem, okay? So this is the probability assignment issue. So in general, we are assigning some probabilities and we are deriving some other probabilities, okay? But this calculation should be, of course, consistent. Otherwise, if you calculate the probability using different ways, if you get the different results, then of course we cannot use that. So to define probability properly, so this is again an extra note, sigma algebra for finite sample space such as our, remember S was die example. So this set has finitely many number of elements. It has only 6 elements. The event space can be defined as all subsets of S. Well, this is very easy to do because it's finite. All subsets of this finite sets, that is, event space consists of 2 to the 6. 64 events. Because all subsets of this, well, I have 64 possible events. So this is rather easy. I should take into account only 64 events. For infinite or infinitely many, and let me write uncountably infinite. So let me correct. For countably infinite and uncountably infinite sample spaces, events should be defined properly such that if A and B are events, then A union B, A intersection B, let's say B complement, should also be events. That means that should also be in the event set, event space. For this one, it was very easy because I have listed all possible subsets. But for the infinitely, as you can imagine, uncountably infinite or countably infinite cases, I should be more careful in the definition of this event. So, for our purposes, this is, well, I'm coming to the conclusion. For our purposes, the events of intervals on the real line, such as minus infinity to A, will be utilized, and it is possible to show that all intervals, all such intervals on real line can be written as union, intersection, and complement operations. This is just a, comment for completeness. So it says that the roots of the probabilities, if you don't have finite sample space, it's a little bit complicated. You have to go into very much details about sets. Okay. So of course we are not assuming such a knowledge, and for many practical engineering problems, you don't have to. You are just using the results of the probability. You don't have to construct this sigma algebra or sigma field. So knowledge of this is enough. So for our purposes, later on I will define immediately random variables. This will be the event of interest for random variables, and of course complement of this union something else will be the event of interest for our purposes. Now let me define then immediately, once I say this, random variable. Okay, so what is random variable? So this is an abstract, let's say this is our sample space. Some events are happening over here. Subsets of this are selected. And this is real line, okay? So events are mapped to this real line. So previously I have faces of the die, okay? You throw the die and you see the face. That is the experiment. So this faces map to, for example, mapping is very simple, number of dots on the die, okay? So if it is 1 dot, you get numerical value 1. If it is 6, it is 6. So let me write 6 over here. So things are, as you see, let me write the origin over here. So this is minus, 2.5. It's a real number, okay? So random variables map sample space to real line, to real numbers, let's say, okay? Or let me, not the sample space, because they are outcomes, because sample space is the whole thing. Outcome is, individual outcome. Okay. Now, how we do this mapping is also an issue, but in general, in electrical engineering, we start with the definition of a random variable. Okay. We are assuming that this mapping is already done in many cases. Like in the die example, you count the number of phases, that's your mapping. But in many other problems, in mathematical problems, you have to, know this mapping to say something about random variables. Okay. Well, that is something, but let me extend this a little further. Now, this is a sample space again. I can also do the following. So the random event is mapped to a point in this x, y, z. So I have, let's say, x naught, y naught, z naught, some point in the three-dimensional space. So as you see, instead of mapping to the real line, so I'm mapping to the r to the power 3, okay, x, y, z plane. So this is called, this is random variable, this is called random vector. Okay. This is called random vector. Again, in general, we start with random vector definition, and in many cases, we don't care about what is going on in the creation of this vector. So we say that, for example, I have a random vector defined with positive entries. Okay, all positive entries. It's called octant in the first octant. Okay. It's generalization of quadrant. Okay. First octant. So this will be the random vector definition. Now what's nice about this? So number of the faces of the die, goal in a soccer match, result of the soccer match, lose, win. Somehow we associate numbers to that. So if we can associate numbers to those outcomes, then we can do some mathematical operations over there. So these outcomes are representing this sample space. So these real numbers are representing these outcomes. But we can also do mathematical operations. Okay. Well, that is it. Now, what else? So I should write my comment. For random variables, so one-dimensional case, for random variables, events are union / intersection of intervals in the form -infinity to a. Okay, a is included. This is our convention. -infinity to a. So I have some intervals on the real line. So maybe this starts from -infinity, goes up to 1, and 1 is included. Okay. So my events are something like that. Maybe if I take the complement of this, there is an open circle over here. I'm looking at the other way around. Okay, this is the complement. I take the intersection of the intervals, and so on. Set operations, as you see over there. Now, this is the event definition, and this is the part where sigma algebra is, used to verify that this is a valid event definition. Let me see what else. Probability assignment. Probability assignment of this, let me use sets. So I have a random variable x. Now this takes values in this, okay? So this x random variable, so this is the set. I'm talking about this set. So this x random variable x is taking values in this set. So again, there is a set. This set is mapped to a real number. Okay. Again, there is a set argument. But since we are already using this, sometimes we denote this by this. Okay. Again, this is also a set argument. Okay. There are some x's satisfying this, and I'm talking about such x's. In other words, maybe I should write this as x. I should write a small x such that x smaller than a and x should be element of sample space. Okay. That is it. Okay. Maybe I should write it in that form. X should be, that is it actually. So this defines a set, as you see. But since we are using, let me erase this. Since we are using random variable x over here, there is a little bit of notational difficulty. So instead of a, we are also using sometimes x. Okay. So what's the meaning of this? Maybe I have many random variables, x, y, z, t, and so on. So you define for each random variable another scalar quantity to define the set. But it gets confusing. X is mapped to a, y is mapped to b. It becomes confusing. To get rid of that confusion, now I have capital X. This denotes a random variable. This denotes, this is not a random, this is something like an a. So this is the ending point of this interval, okay? So this is capital, this is very important, random variable. This is, let me write RV. So this is just a scalar. So the issue is, with this definition, this random variable is smaller than, the value of this random variable is smaller than x. Or I'm considering a random experiment whose outcome is smaller than this x value, scalar value, okay? That is the definition. Now, once you do this, now you define, let me write c.d.f. This is called cumulative density function, as you remember. So what is this? F, this is our notation, capital F, probability of x smaller than x. Okay. This is capital F. So it has a subscript x. This is capital X. Okay. This is small x. So this is the same as this one. So what does this? This tells us that now, so as you see, I can sketch this because it's a probability. And now as you see, since this x is a scalar, it becomes a function. So this x is a scalar. This is a probabilistic mapping, so I have curly brackets still over there because this is a set. But this is not a set anymore, this is just a scalar, so this is a regular function. Okay. So how about this? If I start this function from minus infinity, well, this never happens. Okay. At minus infinity it is 0. And it's monotonically increasing, and it may have some jumps, but eventually it will reach the probability of 1 at some level and stay at 1. Let me say that this is the 1 level. Okay. Do you see why it's oh, this is not monotonically increasing. Sorry. I shouldn't sketch this so slowly. This is increasing like this. Again. But there can be some jumps. Then it goes over here like this. Okay. So this is monotonically increasing. Or monotonically non-decreasing, because it may stay the same as you see over here. But it reaches the level of 1 and you are done. So this x-axis, well, this is the scalar value that I'm talking about. This is the reason, because I'm sketching a function right now. Okay. Now there are issues. This function is right continuous, because at this maybe x0 value, fx x0, you have x0 over here, and that's the reason it's right continuous. Okay. If you go from right, if you approach this x0 from right, you get this value, not the other value. Okay, this is taking, so it's a right continuous, monotonically increasing function. At minus infinity, it's taking the value of 0. At plus infinity, it's taking value of 1. Because random variable is less than infinity, this probability is 1, so when x is infinity, it's 1. Okay. Very nice. So this is c.d.f. Now p.d.f. So these are great ideas actually. p.d.f. Probability density function. Probability density function. So how about this one? Now f x of x, this is just the derivative of this. Okay. Or you may write now the inverse relation. Sorry, capital X, x of x is minus infinity to x, fx, let's say x prime dx prime. Okay. So these are the same relations. You know, one of them is in the integral form, the other one is in the derivative form, and obviously I'm assuming that this density function is taking the value of 0, and that is it. Okay. So how can I show this? Well, if I integrate this from minus infinity to x, okay, if I integrate, so I get this one. So if I integrate this, by definition, I get this density function. Okay. So this is a mistake. F capital X. So this is c.d.f. Okay. This is c.d.f. Lucky we have called that. Now, one more time. If I integrate this from minus infinity to x, I need to integrate this one, minus infinity to x. So this is already in differentiation form. Integral and differentiation operations are, you know, this antiderivative. They are inverse operations. So I get f of x of x minus f of x of minus infinity. But we have said it's equal to 0, so I get this result. Okay, if I integrate this. So both of them are the same. Now, as a mathematician, you may think that how can I differentiate this, especially when is it guaranteed to, you know, able to differentiate this? There are some technical difficulties of defining such a thing, density function, especially at this discontinuity point and so on. But we will, in electrical engineering and so on, we will use our Dirac delta functions and so on, and we will get rid of these difficulties without so much trouble. Okay. Actually, we'll jump over those mathematical definition difficulties. Okay, so this is c.d.f. What else do I have? Let me see. So next topic is independence. But up to now, critical definitions are, of course, these probability definitions, interpretation of sets, these meanings of these brackets, okay, x, capital X, these are very basic. So these kind of relations. But important definition is the concept of density. Density is an interesting concept, okay. So maybe I should write over here. Then, with this density definition, probability of, let me write it as a set, x is element of A, becomes with this density definition. Okay. So what is this A? A is maybe something like this. Minus infinity to 5, union 10, 12, something like that. Okay, so I'm talking about points. Okay, so I have this. I'm talking about, this is capital X, points taking value over here. Okay, over those intervals. So how can I do this? Now this is just an interval, and I can write that interval as the limits of this integral, and that is it. So this is also very intuitive, but it also makes sense. For example, if you don't have this, this is just the definition. Okay, this is the probability definition. So union means if these two sets are disjoint, I should be adding up this probability plus this probability. And as you see, sets are disjoint. So I should calculate the probability of this by this integral, plus there's another integral for this one. And this integral is, if you think about it, it runs from 10 to 12. Because I can write this 10 to 12 integral as minus infinity to 12 and subtract, in a way, set subtraction, minus infinity to 10, okay? So that's the way you calculate these integrals. So I know, so you can write these, all of these things as the integration limits, okay? So let me erase this, maybe just write the result. So if I do this, then this becomes minus infinity to 5 fx of x dx prime, let's say, dummy variable for integration, 10 to 12 fx of x dx prime. Okay, that is it. That is the case. Now there are cases whether this is included or not, but we can discuss those special cases later on. Not important. Let's assume that, you know, this random variable is continuous. Okay, there are no jumps and so on, so this is always correct. The other ways you have to think about Dirac delta functions. But as you see very naturally, you have this. Now this is the density function. I integrate this density function to get this probability value. Probability, as you see, this is probability. So these are, as I have said, disjoint intervals. This is the reason I can separate them. Okay. Now, okay, at this point then let me introduce the following. Now, if I have a density function, actually this is important. This is density function, something like this. It can be 0 at some instances, and so on. So, this is f x of x. Now this area under this density function, as we have said, is if this is, let's say, xa, then this is the area A. Then this A is equal to, as you can imagine, minus infinity to xa, the area under this density function. And furthermore, this is the definition of c.d.f, xa. Okay, that is it. But be careful. Well, many students and some others, they think that the probability density function, the value of this probability density function, for example, at this point, let's say this is 10, x is equal to 10, it takes the value of 1 over 10 over here, 1 over 20 over here. Okay? Many, let's say, students, they think that probability at x equal to 10 is 1 over 20. Well, this is not the case. Because as you see, probability is the area. Okay? Area is this is very important actually. Probability is the area. So this is just the value of this density function. Okay? It's just the value of the density function. If you integrate this density function around this interval, okay, maybe this interval is very short, let's say epsilon, then you can say that, let's say this is B, area B. Then you can say that this B area is approximately equal to, since this density at this point x is equal to 10 is continuous, you can say that the value of this at 10 times epsilon, because this is a continuous function, so this is just an approximation, but the approximation is getting better and better as epsilon goes smaller and smaller. Okay, this is calculus, basic calculus. Okay, so this is the probability, as you see, and I'm talking about area one more time. Okay, so it's very important to understand this. Now, if you check the units, let me write this: density, units, and so on. Now, what do I mean? If this is a probability, this one, A or B, so this is unitless. Okay? It doesn't have the unit of, seconds, meters, and so on. It's just, some set. You are associating a number to the set. It has nothing else. Okay? It's a unitless quantity. So how about this? And how about this, dx? Now, x can be, for example, height of a person, how tall he is. Okay? So this can be in meters. Very funny because, you have some zero probability events over there. Anything. If it is in meters, x is in meters, then this dx is in meters, as you see. So this is in 1 over meters then. So this is density function, 1 over meter. It has to have the unit of 1 over meters such that, this becomes unitless. Okay? Because otherwise I'm running into a difficulty. Okay? So remember, integration is nothing but a detailed summation. So this has a unit, the other thing has a unit. So this is dx is, integration is Riemann integral is f x xk delta. As you see, delta goes to sum. If this has unit 1 over meters, then this has unit meters, then overall sum will be unitless. Okay? So this is very important. Because sometimes, especially if you have multiple random variables, you have to pay attention to these units. If you have dx, dy, dz, and this is the joint density of x, y, z, then you have 1 over meter cube for such a thing. Okay? So when we talk about density functions, even the unit doesn't match the probability. Okay? Unit is 1 over, let's say, the variable, 1 over, meters in this case. Okay. So it's very important to remember this. But in discrete sample spaces, if you have, like in die, then you have, let's say only 2 places. So this is x. Of course, you have this, x is equal to 1. If this is discrete, 0.1. X is equal to 2. You have 0.9. And this is called, a little bit of detail, probability mass function. Okay, probability mass function. Well, this is how these probability masses are, So at this point, it makes sense. Okay, but these are again in signal processing. These are the Kronecker delta functions at 1 and 2. You may say think it like that if these are integer valued, as you see, like that. So this is just like an index actually. So it's like a vector. So this is the first element of the vector, second element of the vector. So this is just their probabilities. But this is very specific probability mass functions. If you are talking about density functions, please pay attention. Density functions are a little bit more complicated. Now, I was going to discuss independence. So, independence, by definition, if you have A intersection B, probability of this event, let me write in terms of sets. We say that event A and event B are independent. B are independent. So sometimes this is like a numerical fact. You calculate this as 0.5, you multiply these two, you get 0.5, you say that, left hand side is equal to right hand side. This is, events A and B are independent. For random variables, now I should define something like this. Capital X smaller than X. Now I should I need a second random variable. Capital Y smaller than Y. Now there is this comma, okay? So this comma means that actually this is an intersection. So this is my event A, this is my event B. Okay? So as you see, this is this A, this is this B. So this comma we don't write, especially when we use random variables. We sometimes, because of that, forget that this is a set operation. Okay. So this is intersection. So you can say how is this happening? Now you have X and Y. So you have some points in, let's say, this is X naught, this is Y naught. So let me say it like this, X naught, Y naught. Okay. Now I have a sample space, generation of these random variables. From the sample space, so this is like a random vector, but two-dimensional vector. Okay. So as you see, from the sample space, I get these points somehow. And the question is, what is the probability that at the end, my XY pair is in this region? Okay. Okay. If you have two random variables, you have a case like that. Now, if you apply this definition, then this is equal to probability of, A is this, probability of Y is Y naught, that is it. But for independence, this should be happening for all. This equality should be satisfied for all X naught and Y naught. So if, let me say star is satisfied for all X naught, Y naught element of real numbers, okay, then random variable X and Y are independent. They are said to be independent. Okay, that is it. So if you have two random variables, let me then define this c.d.f essentially for this. This is the extension of the one-dimensional, well, if you forget about Y, this is the extension of, X, comma, meaning again intersection, as we have said before. I have something like that. Okay. And I can define the density function . Now, since I have two random variables, I have to take the derivative twice. Okay. So this is the density function. Now, so this is the, sorry, again I make that same mistake. This is the c.d.f function. So if I take the c.d.f function, take its derivative with respect to x and y, so I am done. Okay. Again, what are the units of this? If you think about the units, well, if this is meter, this is meter, I have meter square over here. This is probability, this is unitless. Okay. So this is like numerator is, unitless 1 over meter square. So this density function, something like that. Okay. That is it. So units are very important and they always come up in our calculations. You may take this as definition because we haven't thought about it so much. Now, units. Next, but you may maybe appreciate it, instead of one-dimensional integration over a real line, if I have two random variables, now I'm integrating, wow, now over minus infinity to x minus infinity. Let me then move this y, this is x, something like that. Okay. So I'm integrating this time over this area. So I have this density function. Density means, around this, for example, I'm interested in xy pairs over in this blue area. So there is this height above this blue area. This height is the value of this density function. So I'm calculating this time the volume of this, three-dimensional figure whose bases this blue part. So, for example, if the height is something like this, tip of this board marker, so I'm calculating this volume, okay, over here. This is this calculation. But, of course, I'm calculating the volume from minus infinity to x, minus infinity to y. So I'm calculating, this is the base area, the volume over this red part. And that becomes, you know, two-dimensional or joint c.d.f. for x and y. This is extension of one-dimensional idea, one more time, to two dimensions. Now, I want to discuss, these are all nice. So this is something interesting. Now, something actually critical. Conditional probability. By the way, these topics in an ordinary course are taught in several weeks. In EE 230, for example, coming to this point takes maybe, I don't know, maybe one midterm time or more. Okay. Now, conditional probability, probability A given B. So what's the meaning of this? Well, its meaning is probability of A, this is a set, probability of outcome is in A, outcome is the result of the experiment, given that outcome, given that means I know that outcome is known to be in B. So maybe this is something like this. Probability that this a little bit out. I won't be using outcome. A happens given that B has happened. Okay. So, for example. One of the soccer teams will be the champion, probability that soccer team 1 will be the champion, given that the other team has lost the match, okay? So, you have some additional information, given that the other team has lost the match, probably this team has a higher chance of being a champion, isn't it? So, it's something like that. So, there's an outcome, there are two different sets, and so on. So, what's the meaning of this? This is actually the main thing, conditional probability. Now it means the following. Now, let's say it's my sample space. So I'm defining a random variable over here. Let's say this is origin. There are some mappings like this. This is mapped to -10. This is mapped to 1, or this is, let's say, 6, 2.5, and so on. Now we are interested in the following. Probability of x element of, let me see, -2 and 2, given that x is greater than equal to 0. Okay. So what's going on? So how can I know this event, I know this other event, but something has happened. How can I take into account that? That is the issue. Now the issue is the following. We are considering the sample space. So somehow I'm generating these x's from this sample space. But I know that at the end of this generation, my x turned out to be positive, meaning that I'm on the right-hand side of this line. So I'm eliminating, maybe these ones are, and also this one. Which one is this? Oh, this one. Not this one then. This one is mapped from somewhere else. Let's assume that all of these ones are generating, this one is always negative valued random variables in this blue part. Okay? They're always generating blue valued random variables. non-negative valued random variables. Okay. Now, what I know is that in the sample space, this event can occur with some probability, but what I know is that now these events have not occurred. So I should be focusing on the other events. So you may now consider this. After this conditioning operation, now there is a change in probability assignment. Now all of these outcomes in this blue area after this probability assignment, they are just eliminated from our sample space, or they are just taking the value of 0, probability of 0. Now our sample space is essentially reduced to this. Okay? Reduced to this red part. Because I know that this has happened, so none of these events will be contributing to my probability, so I should be focused on this red part. So then, how can I do this? Well, here is the definition. So this is the actual definition. If I call this A, if I call this B, probability of A intersection B, probability of B. Okay? So if so this is probability of A given B again. Okay? So if I write in terms of X, probability of X, element of minus 2 and 2, intersection X greater than or equal to 0. Okay? So as you see, I have a set, another set, their intersection, divided by probability of X greater than or equal to 0. Okay. So in this case, if I do this, probability of X, if you take this intersection, X element of 0, including 0, up to 2, divided by probability of X greater than 0. This is our definition, okay? This is the way we define. Well, in other words, we are looking for, A intersection B. Maybe, let me have another color. I think it's very obvious, but let me at least say it. So, let's say that minus 2 to 2 interval is formed by this green part. So green part is mapping this. So this is doing the following. A intersection B. A intersection B is X greater than 0 is the red part. So this is A, green part. But I know that, I should make this a little different, green part, because this green part also includes negative valued quantities, as you see over here. So this is A intersection B, divided by probability of B. So you can wonder why I'm dividing by probability of B, but I think it will be clear immediately. Now, this probability value, okay, let me say it like this. Instead of 2, let me explain it this way. If I insert, let me move it over here. If I insert instead of 2 an X, I'm just making it a random variable right now. Okay? Not a probability calculation, but this is just an X. Okay? So this is then X. X can be a variable. If X is equal to 2, I get a numerical value. If X is a variable, then this becomes a probability calculation. Okay? Then as you see, what do I have? If I increase X, so this is minus 2 to X. If I keep this increasing and increasing and increasing, so what happens? So I see the following. So at the end, this calculation will be from 0 to infinity. if I keep on increasing and increasing and increasing. So what I see is that several things at the end of this calculation. If I have a random variable defined like this, if I do such a conditioning, again, after this conditioning, A given B, let me call this is, or let me write this, sorry, x minus 2 to 2 given x greater than 0. Let me write this small x. If you consider this random variable as, let's say z, this is, oh, let's do not introduce anything else. So this is a random variable. After this conditioning operation, you can see that is a valid, has a valid probability density function, okay? Or let me say c.d.f function, because we have seen c.d.f function. In other words, if this x is, for example, minus infinity, you get 0. If this x is equal to minus 1, you get 0. If x is a positive quantity, now you get some positive values over here. If x is infinity, you get 1. Okay? So, with this definition, you immediately see that at least, you get some insight why you need this division. Okay? To be consistent in these, random conditional probability definitions and so on. Now, if I am done with that, let me see conditional probability. Now, this is also important, and we will be ending our lecture after this. Now, we have seen the following. These are definitions, but it seems to be a useful definition. At least in the generation of this conditioned random variable. So I have Bayes' theorem, but so I'm not doing anything but writing this definition one more time. A given B, B given A. So just pure mathematics. Now I get this. Probability of A given B is equal to probability of B given A times probability of A divided by probability of B. Okay? So what is this? Well, if you check this, this is the common term. Numerator is the common. If you multiply by PB, if you move this to this side, then you have A intersection B probability over here, and this is also A intersection B probability. So this is called Bayes' theorem. This is a little bit surprising. It's an immediate result of conditioning definition. Okay? Well, why it is a little bit surprising? As we have explained, this A given B corresponds to elimination of some parts in the sample space and so on. So this is the other way around. Okay? But we are seeing that these eliminations are, after this probability assignment, they are interrelated. Okay? So in many probability calculations, maybe you are interested in this event, but this is difficult to calculate. Then you calculate this, and these are rather easy. Okay? So you see that because of this equality, you can get the other one. Okay. What else? Okay, let's keep it at this point for today. We will continue from this point on in the next lecture. Thank you so much.